Okay, welcome back. So in this video, we are just running through some examples using the chain rule, and let's just jump right in. So first we're going to find the derivative of e to the 3x. So remember, for chain rule, we need an inside function and an outside function. And part of why I know that I need to use chain rule here is that this is like e to the x, but it's not just e to the x, it's e to the 3x. So this isn't just a standard derivative that I know. I know the derivative of e to the x, but I don't know the derivative of e to the 3x yet. So this is a composition, and I'm going to need to use chain rule in order to take its derivative. So before we jump in, why don't you try and see if you can determine which function is the inside function and which function is the outside function. So here I have e to some power. That power is 3x, so 3x is my inside function, and the outside function is e to the x, or e to the something. And we can check that this works by thinking of putting the inside function in as the input. So we have e to the power is 3x. Okay, so the inside is g, the outside is f, and I'm going to need their derivatives, so let's just go ahead and find those. The derivative of 3x is 3, and the derivative of e to the x is itself, e to the x. Now, using chain rule, the derivative of a composition is f prime of g of x times g prime of x, where the composition is f of g. So I like to work from the inside out with my inside functions first. So f prime of g is 3x, then I multiply by the derivative of g, that's 3. Now I need to look at what is f prime of 3x. So f prime, the function just takes e to the input, e to the x. My input is 3x, so I have e to the 3x, and then still times 3. And just rewriting this, I have 3e to the 3x as my derivative. So as we get more comfortable, you can do this a little bit faster by just remembering that the derivative is the derivative of the outside, with the inside left alone, times the derivative of the inside. So here I'm thinking of my outside function as e to the x, so the derivative of e to the x is just e to the x, and I leave the input the same, the 3x, the inside left alone. Then I multiply by the derivative of the inside, the derivative of 3x, which is 3. Then simplifying, I can rewrite this as 3 times e to the 3x. Alright, so that is our first example. We have found the derivative of e to the 3x, and it is 3e to the 3x. Let's try another example, and I'll give you a shot to try this one on your own. Okay, so let's say we have a function m, and it is the square root of x squared plus 5. And we want to find the derivative with respect to x of m as a function of x. So let's pause. I want to see if you can determine what is the inside and what is the outside here in our function m of x. Then if you want, you can continue and try to find the derivative using chain rule, or you can come back and we'll do that part together. Okay, so something that I think is going to be helpful here is just to remember that we can rewrite a square root as everything to the 1/2 power. So as we do this, I'm going to just write everything in both ways just to remind us that we can rewrite the square root as that 1/2 power. Okay, so I'm seeing that we have the square root of something, and that something is x squared plus 5. So I'm going to say x squared plus 5 is my inside function, and then square root of x is my outside function, or x to the 1/2. And we can check that this makes sense by thinking that the square root of x is like the square root of something, and if we put the inside function in as that something, we're getting back square root of x squared plus 5, which is what we want. Then again, the inside function is g, the outside function is f, using my formula for the chain rule, and then I know I'm going to need both of their derivatives, so I'm just going to go ahead and find those now. So the derivative of g is 2x, and for the derivative of f, we're going to use that x to the 1/2 version and apply power rule. So the 1/2 comes in front, then I decrease the power by 1, so we do a half minus 1, which is negative 1/2. And then to help us out, I'm going to rewrite this using positive exponents. So we can bring the x into the denominator and then make it a radical again. So this is 1/2 times the square root of x is our derivative of f. Now let's put this all together. So the derivative of m is f prime of g of x times g prime of x. That's our chain rule. I'm going to start with my inside functions. So f prime of g is f prime of x squared plus 5. Then I multiply by the derivative, which is 2x, the derivative of g. Now I just need to plug in that x squared plus 5 into the derivative of f. So the derivative of f is 1 over 2 times the square root of the input. My input here is x squared plus 5. So I have 1 over 2 times the square root of x squared plus 5. And this gets multiplied by that 2x. And now I just need to simplify. So I'm seeing that those 2's will cancel. So I'm left with x over the square root of x squared plus 5. And we found our derivative. We found the derivative of m. I'm going to do this with every example, but once we get more comfortable, we don't have to always write out the inside and the outside functions. We can just think that the derivative of a composition is the derivative of the outside function, with the inside function left alone as the input, times the derivative of the inside function. So here, my outside function is like the something to the 1/2 power. So I'm going to use power rule on that. The 1/2 comes in front, I leave the inside the same, and I decrease the power by 1. Then I multiply by the derivative of the inside function, the derivative of x squared plus 5. Then to simplify, I know that the derivative of x squared plus 5 is 2x. I can cancel those 2's out, bring the exponent into the denominator as a positive exponent, make it a square root, and I'm left with x over the square root of x squared plus 5. There we go. That is how we find this derivative using the chain rule. Alright, well thanks so much for watching, and I will talk to you in the next one.